Namaskara. Warm welcome to the course on intermediate algorithm. You might have already done courses on discrete mathematics, data structures and programming, and even introductory course on algorithms. Typically in an undergraduate course, in order to give the coverage at the introductory level, most of the advanced concepts associated with them, the rigorous mathematical details of the analysis and other things wouldn't have been done. And the purpose of this course is to provide a comprehensive and complete overview of such missing pieces. It will also take you to the next level of understanding, working with the mathematical details, conceptual foundations and so on. So algorithms being at the heart of computer science, building competence in that at various levels is important. At the first level, you get a nodding acquaintance, you write a program implementing it and so on. At a higher level, you do a careful and detailed analysis and you look into the various ways in which it can be extended, modified, applied and so on. So in order to go through variety of these coverage, I have formulated this course, okay, which allows us to dwell in depth. Okay. At the same time, in order to make it accessible and reachable, we want to distinguish this from an advanced course on algorithm, which will have more advanced topics and the same topics covered at a more advanced level. So this is an ideal next level course for those who are excited about learning on algorithms. Once again, warm welcome to you. When we try to solve the real world problem, we start with what is known as mathematical thinking. Okay, so paradigms. Algorithmic paradigms. We start with mathematical thinking. In mathematical thinking, we derive various properties related to the math problem. We derive characterization, upper bounds, lower bounds, possibility result, impossibility result, uniqueness and theorems. Okay. So basically you derive a lot of properties in the context of the problem. Okay. How do you convert these properties into process? That is computational thinking. CT is computational thinking. You have some properties and based on that you can say that I can do this, this and this and then obtain an answer. So you must come up with a computational method. A computational thinking is attempting to build a solution through an explicitly computable steps. In other words, the math world will have certain operations. You do the series of operations and then obtain a value, construct an object. For example, if it is a shortest path problem, you have to physically construct the shortest path. If it is matrix multiplication, you have to physically obtain the values of the entries or the product and so on. So how do I explicitly obtain it? You may have certain properties that's completely different from an explicit way to obtain them, and that is computational thinking. So computational thinking can also be viewed as constructive problem solving. You try to solve the problem in a constructive way. Okay. So in computational thinking, what we do is we perform a series of operations and perform a series of operations and construct an object with certain properties or obtain some value and so on. This is what we do. For example, if it is a shortest path problem, we have to obtain the shortest path. Okay. So basically we will see, we think about, in computational thinking we think about how to convert properties into a process, a computational process. How do I compute, how do I convert characterizations into computations? You have theorems saying that this is true or this object has the property if and only if. That is a characterization, that is a mathematical characterization. But how do you use it to verify and then actually obtain the object with certain properties? Okay. So how do you convert characterizations into computation? These are all coming under computational thinking. Computational thinking is very essential because now you see the whole thing as a process. From this we mature to algorithmic thinking. In algorithmic thinking, we are focusing on efficiency. It is computational thinking plus efficiency. AT stands for algorithmic thinking. In algorithmic thinking, it is computational thinking plus efficiency. That is because we are trying to use algorithms to solve the problem by using computers. So this is basically problem solving by using a computer. That is the reason why we have a focus on efficiency. A computational solution or a constructive solution, in fact in the mathematical world and to the mathematicians, as long as it is finite, they are happy, it is doable. In principle we can do it. That is how mathematicians would put it across. In principle we can do it because it is finite. But when you are actually trying to implement it on a computer, if it takes 300 years or 400 years to compute, okay, even with the help of a fast computer, if it takes, that is not a practical solution. It may have a finite number of steps, but that finite number is too large. So in algorithmic thinking, we attempt to figure out how to solve the problem more efficiently. And we also ask the question, is it solvable at all efficiently? All these kind of questions come under algorithmic thinking. In the introductory part, an algorithm will be presented and a simple analysis will be done. But now, since algorithmic thinking requires you to take a closer look at things and then look for scope for improvement and then reduce the unnecessary computations or coming up with alternative ways in which a more efficient solution can be obtained and so on, it is a very creative process. That means we have to take a closer in-depth look at the algorithm design and analysis. That is exactly what this course is attempting to do. We will start with something all of you are familiar with, and then we will see how a closer look at that is really helpful in getting better understanding of the whole design process and also the properties of the algorithm itself. So we illustrate all these things with the help of studying the problems that we solve under one particular idea. Okay? By paradigm, we mean a pattern of computation in computer science. Paradigm, the word paradigm has got different meaning in different contexts, but in computer science, it is a kind of a pattern of computation. Okay? It is derived from the Greek word paradigma, externally displayed example, to show a pattern. So basically, It's a pattern of computation. Here is the pattern of computation for divide and conquer. You have an input I and you split the input in two parts, I1 and I2. Solve I1 and I2 and obtain their solution S1 and S2 and find the solution of the original input. This is the so called computational flow. This is how the computation is done. Obtain the solution of the original input by combining the solutions S1 and S2. So, you are going to work with S1 and S2 to generate S. You are not going to work with I directly and then work on it and then straight away go to produce the solution. First you split, solve independently, use the solutions to combine. So, the divide and conquer will have three visible phases in the general form: the divide phase, the conquer phase, the merge phase or marry phase, putting the solutions together to get the solution of the original input. It is a generic form. This is a pattern of computation. Okay? And the divide and conquer algorithms is carrying in it the quintessence of algorithmic thinking, the way in which it is bringing in efficiency is amazing. Okay? So, this is the divide and conquer paradigm. A canonical example of the divide and conquer paradigm is merge sort. Merge sort has got an interesting historical background. Back in 1940s, computer organization, architecture and computer design were all in the nascent stage. EDVAC was one of the early days computer, and von Neumann was appointed as a consultant for this project. So, he has come up with an instruction set and designed the architecture for this, and then he has also come up with an instruction set for this one, and he wants to prove that prove its efficiency. It is a government funded project and you are going to get additional money only if you prove that this is indeed a worthwhile project and this system and this design is functional, efficient and so on. So, he has the task of establishing the merit or the efficiency of this system. So, how to demonstrate that this is a good system, it can solve problem and do computations in a very efficient manner. So, he has taken up the problem for sorting. Okay. Sorting is not number crunching, it is involved comparison and basically has got logical operations to carry out, relational operation to work. It is not number crunching. In other words, it is the logic that guides the solution. Secondly, at that time there was a special purpose sorting machine available. The census data and other things were all processed using the Hollerith machine, a special purpose machine, and that will do sorting and collating, okay, of the data that is that was there in the punched cards. So, a collator is going to take 2 decks of cards that have got sorted data and then it will merge them into a single deck of sorted cards. Okay. And it was a very efficient one because it was doing it in one pass, a single pass algorithm, and that is what is discussed even in the classroom for merging two sorted sequences. The algorithm that was used in IBM collator is what is used. So you have a special purpose machine available, and here is a computer. It is a general purpose machine, but it can be programmed, and I can get a performance better than that, right? He has to now prove that this system can beat a system that is beat a system that has a special purpose designed for the sorting problem. Okay. So he designed the merge sort algorithm and implemented it, and then compared its efficiency with the performance of the special purpose machine. This turned out to work way faster. He is also the pioneer of a stored program concept. So he has used the instruction set that he has devised, the stored program concept, and the hardware, and very importantly the algorithm for sorting, a clever algorithm, efficient algorithm. He needs something really efficient. Had he chosen some inefficient algorithm or a naive algorithm, and if it didn't perform well, the whole project would have gone flat. He has chosen a very clever method to solve the problem. He has created. Merge sort is created by him, and it is based on the divide and conquer paradigm. Note, a great computer scientist who is alive, okay, calls this as a historic moment, right? The moment where merge sort program was implemented, created, and then it created an impression. And in the history of computer science, the merge sort algorithm and its creation and implementation is considered as an historic moment, amazing moment. It's such a great historic background you have for this. Okay. So merge sort, I'll put it in a very simple form. The pseudocode and other things I will give it in simple form, because you are perhaps very familiar with it. So let me merge sort A 1 dot n. This is an array of n elements. Here we are considering them as n integers. N is the number of items, size of the array. Okay. If n is greater than 1, well, if n equal to 1, there is only one item. Sorting one item, just leave it as it is, don't do anything. There is nothing need to be done for sorting one item. So only if n is more than 1, you have to do the divide and conquer. If n is greater than 1, let q equals floor n by 2. I will talk about floor ceiling a little later. Okay. And merge sort A 1 dot q, and this has got q elements, merge sort q, and merge sort A q plus 1 dot n, and this has got n minus q elements. So you are solving the problem for the first half. You have sorted the first half, you have sorted the second half. Now merge the two sorted sequences. Merge the two sorted sequences, A 1 dot q, A q plus 1 dot n, and you are done with. So divide, conquer, merge, canonical example, very typical example of a divide and conquer algorithm. Okay? Let us see some interesting points here. The first thing is the mathematical detail. When you are trying to split n objects into two sets, to begin with, we will try to split them as equally as possible. If you have 40 items, you can split as 20 and 20. If you have 41, how will you split? In two equal parts. You can only split nearly equal part. That is where the floor function and ceil function comes into picture. So, n by 2, for example, 41 by 2 is 20.5. So, when you take floor, this is 20. When you take ceil, 41 by 2, this is ceil of 20.5 and this is 21. So, 20 is just the previous number and 21 is just the next number, because 41 by 2 is not an integer, it is a real number, 20.5, but we are going to split in size, which is an integer, two subarrays. So, one will have 20, another will have 21. So, we will have the following fact: floor n by 2 plus ceil n by 2 is n for all n. For all n, this is true. Okay? You can prove this in a very simple manner. Okay? Consider the case when n is odd, consider the case when n is even, and very straightforward proof is possible for this fact. So, you are going to split in two parts. One part will have q equal to floor n by 2. Therefore, n minus q, because these two add up to m, is ceil n by 2. So, you are splitting the problem into two parts. One part has size floor n by 2 and another part has size ceil n by 2, floor and ceil function. The merging problem is the following. Okay? You are given two sorted sequence, let us say two sorted sequence A and B. Size of A is, let us say, n, size of B is, let us say, m. Therefore, size of C will be n plus m. You are given two sorted sequences A and B. A and B are sorted. A and B are sorted, and you are given two sorted sequences, and you have to produce a sorted sequence made up of the elements of A and B. Put all the elements of A and B together and form a sorted sequence. That is the reason why C has n plus m numbers and it is a sorted sequence. So, input two sorted sequences, output a single sorted sequence consisting of all the elements in A and B. There is a single pass algorithm, well known algorithm for merging, and its complexity will be n plus m minus 1. This is the worst case complexity of merge algorithm. This is the worst case complexity. Okay? N plus m minus 1 is the worst case complexity of the merge algorithm. Now, we can analyze the merge sort and obtain an estimate for the number of comparisons done by the algorithm. Let Tn denote the number of comparisons number of comparisons done by merge sort on an array of size n. Okay. Actually, this is the maximum number of comparisons. This is a worst case complexity. So, denote we will say maximum number of comparisons. That means Tn stands for worst case complexity. Tn stands for the worst case complexity of the algorithm. Let Tn denote the maximum number of comparison done by merge sort, okay, on an array of size n. Now, the execution of the merge sort, you first run on the first half, and how much time or what is the complexity of the first recursive call? That will be T floor n by 2. This is the cost of or complexity of first call, and T of n minus q, we have seen it is ceil n by 2, T of ceil n by 2 is the complexity of second call. Then you are merging. You are merging two sequences. One is of size n by 2, floor n by 2, another is of size ceil n by 2. So, complexity of merge is floor n by 2 plus ceil n by 2 minus 1, that is equal to n minus 1. So, let us go back and then so the complexity of merge sort, this is T of n, this part is T of floor n by 2, this is T of ceil n by 2, because n minus q is n minus n by 2, which is ceil n by 2, and the cost of this one is n minus 1, that actually floor n by 2 plus ceil n by 2 minus 1, which is equal to n minus 1. Therefore, you conclude from this that T of n is T of floor n by 2 plus T of ceil n by 2 plus n minus 1 if n is greater than 1. If n equal to 1, it is 0. It is 0 if n equal to 1. That is because when n equal to 1, you do nothing. There is only one element, sorting one element, no comparison, nothing is done. Therefore, the complexity is 0. The number of comparisons is 0. So, T of n denotes the worst case complexity function, but it is in recursive form. We want T of n in closed form. Closed form means a direct formula of n, right. A function like f of n equal to n square plus 5n plus 3, this is in closed form. The value of f on any integer can be directly computed by substituting the value in that formula. You can't do that here. For any recursive one, you have to keep recursing, and then only you can find a formula. And when a function's specification is in recursive form, you can't compare with other one. Suppose I tell you that the complexity of insertion sort is order n square. This is the complexity of merge sort. Is it better or same or worse? How do you compare T of n with the complexity of insertion sort? Complexity of insertion sort is say order n square. How will Tn be compared with this n square function? It is in recursive form, so you are helpless here. That is the reason why we need T of n in closed form. The mathematical details related to that is very important. Okay? So, we will take the following approach. The complexity function for merge sort is given by the recurrence equation, and we are interested in finding the closed form for T of n. We conclude this session at this point and continue the discussions on the derivation of closed form in our next session. Thank you.